Thank you, Ellie. So I realized I didn't properly introduce myself earlier. So once again, my name is Sebastian. I'm the host of a couple of podcasts that some of you may be familiar with. Epicenter, which has been around for a long time and has greatly contributed to my knowledge and understanding about crypto. And another podcast called The Interrupt, which I launched recently, which is more focused on the Cosmos ecosystem. Which brings us to our next guest, Adrian Brink, who is the co-founder of Anoma. They're building a general purpose chain to allow folks to trade on... Right. On intents. So please give a round of applause to Adrian for his talk here on Anoma.
Thanks. Cool. All right. I was told to stand over here, is that still correct? Okay, cool. Hello, welcome. Thank you very much for coming. I'm Adrian. I'm one of the co-founders of Anoma. And today I just want to give you a brief introduction into what Anoma is, because at a very high level, it's a unified architecture for full stack decentralized applications. And I'll go more into depth what that means. So I want to start with a brief historic recap of sort of where we started from, where we are today, and I think where we are going to go. And I think a lot of other people look at the evolution of blockchains very differently than I think we do at Anoma, which is they sort of think of consensus improvements were evolutions to blockchains. But I want to present a different view or a different segmentation to look at the evolution of blockchains. So the first evolution really of the first generation was really Bitcoin and scriptable settlement. And here the main part is scriptable settlement, which was non-Turing complete. Some programmability is accessible. You can have some smart contract, some multi-sigs. You can start hacking around with applications that you may think would look cool, like colored coins or named coin. But the first generation was very clunky. Like building colored coins on Bitcoin is incredibly difficult. And as a result, it sort of never took off really. And we ended up getting Ethereum. Same for Namecoin, right? Like Namecoin is the original ENS really, but it required a fork of the Bitcoin client. Because fundamentally, scriptable settlement just has downsides. It is not as flexible, it is not as easy to use. And so as a result, we ended up with Ethereum. And the funny thing is actually, Vitalik talks about this in the white paper, how scriptable settlement wasn't enough. And so Ethereum, the second generation, gave us programmable settlement. And all of a sudden, we didn't have to be OK with just having colored coins. We could have ERC20s, and they were very easy to develop. They were very easy to integrate with, and all of these nice things. We also, instead of having Namecoin, we got ENS. But importantly, we also got a host of other applications that we didn't consider when Ethereum was created, right? Like we looked at what is currently being built on Bitcoin, and can we make this better? And so we ended up with programmable settlement. But we didn't think of sort of all the future kind of applications that would fall out of having a very general programmable settlement architecture. So we got DAOs, we got new kinds of assets like NFTs and soul-bound tokens. We also got a bunch of like other modern applications that we didn't think about when Ethereum was created, but which sort of like as a result, all of a sudden became doable. And so I think one of the good examples here is like modern DEXs, AMMs, NFT marketplaces. But I think in the same way that colored coins on Bitcoin had trade-offs, NFT marketplaces and DEXs, like the modern applications on Ethereum, have trade-offs as well, which is predominantly that they generally require at least one, if not more, centralized Web 2 components in order to make them work. Right? When you think on, and most people don't think about this very deeply, but when you think about what OpenSea does, OpenSea just accepts a bunch of signed messages, does some compute, and then ends up settling this on Ethereum. But like you fundamentally, as a user, you're sending these signed messages to a centralized Web 2 server running under a single IP address run by the OpenSea team. And so this is like the centralized component. CowSwap has the same thing. There's a centralized solver. most of the actually all of the rollups, whether optimistic or zero knowledge, have this as well. You send some sort of signed transaction to either the optimistic the optimism solver, optimism sequencer, or you send it to the Starknet solver, prover, sorry. And of course, we had a bunch of other things that people traditionally refer to as evolutions of blockchains. But I would say they're like second generation plus. They're still programmable settlement. We made advances in Sybil resistance, we got some advances in scaling, we made advances in privacy, we made leaps and bounds in terms of underlying consensus mechanisms like Tendermint, Avalanche, and eventually ETH2 single slot finality, but it's still fundamentally programmable settlement, as in the underlying model that is exposed to developers doesn't really differ whether this is on Ethereum or on Near. It's always a imperatively executed VM that runs in a different color. And maybe the color, like Near is now green and Ethereum is yellow, and the color determines like speed and finality, but in the end, you're writing the same kind of smart contract. You're building the same kind of application. Very similar to like how you had a long tail of Bitcoin forks, how we had a long, sort of a vast swath of scriptable settlement chains. Right. Yes. So, I want to start with that settlement is not sufficient. And this is what programmable settlement does very well. Programmable settlement does settlement, but just settlement. Settlement is only applicable once parties know who they are, with whom they want to coordinate, and exactly what they want to coordinate on. When you actually look at pretty much 99% of all interesting applications, they need counterparty discovery. Like OpenSea, you don't directly interact with a protocol. Like you don't directly interact with Ethereum because you don't have a finalized state transition. You have the idea that you want to you currently hold, let's say, 1 CryptoKitty, and you are willing to hold 0 CryptoKitty if you hold some ETH, right? But you need to find a counterparty with whom to settle this on chain, or you need to find multiple counterparties. And so we need infrastructure that can help counterparties discover each other and also agree on what to settle specifically. We see this in a ton of places. We see this in the marketplaces where you need buyers and sellers. We see this in the quadratic public goods funding where you have project donors and funders. We see this in the DAOs where you have voters that all need to coordinate to then have a sort of resulting state transitions being settled. We even see this in rollups, because what is a rollup? Like someone signs a message, they send it to a server, that server does some compute, and then the resulting computational output gets settled on chain. This is the same between optimistic rollups or zero knowledge rollups. It's always this model that we fundamentally need somewhere to find counterparties and agree with these counterparties on exactly what to settle. There are like a very few exceptions. Like if you want to send money to yourself, if you like have some ETH and want to have some private ETH, then you maybe don't need a counterparty because you can just directly go into a shielded pool and go out to yourself. But even if you are thinking of, I don't know, like buying a bottle of water, there's a counterparty discovery step where it's like you have to figure out who's selling a bottle of water and how do you agree on the pricing. So pretty much all of human interaction requires counterparty discovery because very few things happen in isolation. So what have the contemporary approaches to counterparty discovery been? Well, sort of the current thing we're doing is to do it on a blockchain. This is what an AMM does. This is also what an on-chain order book does. I have to say though, this is very expensive because you have to put everything in consensus, and you have to pay gas for this, and you have to pay for the privilege of establishing a total global order over all those messages. And it's actually really silly because there's almost no point in sorting all these messages and establishing a total order for them. But I have to say AMMs are sort of the best answer to this question on how do you currently do decentralized counterparty discovery. And yes, you chuck it all in a smart contract on Ethereum, and that smart contract does all the counterparty discovery and solving for you. The other approach is you run a single operator database. This is, outside of Uniswap and the AMMs, by far the most popular way because it is very easy. Because you just centralize the entire thing. You say, oh, I'm OpenSea, I'm going to run a single server that accepts all messages, then does some compute over, let's say, 100 signed messages and only settles the sort of matching messages on Ethereum. This is what the 0x relayers did. This is what Flashbots does too. Like the pattern is always people have intents, they send it to some counterparty that then they do some compute, and then you settle the resulting state transitions on chain. Rollup sequences already spoke about this. But the important point to remember here is these are trusted parties. In the best case, they can't steal your money. But in almost all cases, they can end up censoring you because, right, they can just block the IP address you're coming from and not relay your message, not take your message into consideration. You also get very few fairness guarantees on, let's say, 5 of us are sending a message to OpenSea. There's almost no guarantee that OpenSea isn't front-running all trades because we don't get any sort of ordering established that is relative to each other. This is not about the total order. This is about a relative ordering between our messages. And then the third approach right now is sort of you build an app-specific sovereign chain. DYDX is doing this at the moment. A bunch of other things have done this as well. The problem is there are also trade-offs. You lose composability. All of a sudden, the signed messages aren't composable with each other, which is one of the very nice features of actually programmable settlement on Ethereum is that smart contract calls are composable with each other. But so if you put this on an app-specific sovereign chain, you lose this composability aspect where I can't reason through the intent that I've sent to OpenSea and the intent that I sent to 0x, and I can't compose and settle them in the same state transition. Also, this requires a ton of dev work because you're building your own blockchain. So I wanted to use what I would consider the third generation of protocols. And Anoma is an architecture. This is important to understand. Anoma is an architecture with many different deployment models. You can deploy Anoma to Ethereum as an L2. You can deploy Anoma as an L1.5 to decentralize a specific dApp on Ethereum or a dApp on some other system. Or you can deploy the Anoma architecture as an L1, as a sovereign chain. So yeah, to just repeat this, Anoma is a unified architecture for full-stack decentralized applications. And now I'll sort of take the remaining time to go into what this actually means. So, in a nutshell, it's an intent-centric, privacy-preserving protocol for decentralized counterparty discovery, distributed solving, and atomic multi-chain settlement. I'm not going to go through all these words in the next couple of minutes. I'll very much focus on intent-centric and the privacy-preserving part as well as the counterparty. But atomic multi-chain settlement is a whole other beast. If you're into consensus mechanisms, I recommend to check out heterogeneous Paxos or our implementation thereof, which is called Typhon. It allows you to do cool things like have the ability to have 2 separate blockchains that have an overlap in their validator set to form a virtual shard at runtime so that you can have atomic transactions between those 2 blockchains, even though for most of the time they're running as separate sovereign chains. So the key design principles driving the design of the Anoma architecture are intent-centricity and homogeneous architecture, heterogeneous security. So intent-centricity is really that users express what they want, not how to get it. This is very different than every existing blockchain is constructed because every existing system has the primitive of a transaction. This is sort of the fundamental base unit. There's a transaction that executes some state change on a system. This is not what users have. Users have partial transactions. They have intents. They have like, I want to hold 1 less Bitcoin if I hold 100 more ETH, right? Like a simple trade. They can't settle it themselves. They need to find someone else that matches that inverse. And importantly also, currently users express like what a transaction does on, for example, the EVM. It authorizes an execution trace, right? Like when a user submits a transaction on Ethereum, they're not saying that they are fine with some future state. Like they are fine with holding somewhat tokens if they hold some less tokens of some other thing. They are saying that they're okay with this entire execution trace of like smart contract A calling smart contract B calling smart contract C. And this is terrifying from a user perspective because to be secure in these systems, you need to reason through the entire execution trace because any intermediate proxy contract can change arbitrary amounts of state. And you never said what state you are fine with. You only said which contracts you are fine with doing some compute on your behalf. This means that honestly, if you want to use these systems securely, you need to audit every single contract call that is in your transaction in order to be actually certain what it does. Whereas with intents, people just define what resulting state they're fine with, and then it's the job of the system to figure out how to get them that state. And the end step is not that you've authorized some execution trace. The end step is that after the system has figured out what state changes or what execution trace to take, every user's validity predicate just verifies that their state changes weren't violated, that the state changes they authorized were actually implemented. So intents are binding programmatic commitments to state preferences. This is really the way to think about this. The really nice thing about intents is that intents don't have to be globally ordered, so they don't have to live in consensus, because they're not fully fledged state transitions that have to be reflected globally. There can be a P2P intent gossip network that can have 100 billion intents. And not everyone in the world needs to have the same view of this network. As in, I can have a different view of a subset of the network, and someone else can have a completely different view. There may be some overlap, but there doesn't actually have to be any overlap. As in, every person that views this network can filter for their own kind of intents that they care about, which makes it very scalable, because you can have an intent gossip network that spans multiple blockchains at the same time. So now we have all these intents, right? We have 100 billion intents. Now there's a component called solvers. Solvers effectively look at the soup of intents, and they see which ones are compatible. And if the solver finds, let's say, 2 intents that are compatible, they can bunch them into a transaction and submit them to the settlement layer. But it could also be that they take 5,000 intents and settle them into a transaction, and create a transaction and settle this on-chain. This is really important because it allows us to do very cool things like ring trading, where it's like some user wants A for B, someone else wants B for C, and a third person wants B for C, right? Like, we don't have to trade the entire circle. We can just net out the changes on the intent level, combine them, and settle only the resulting state changes, because users didn't authorize the specific execution trace. They authorized what state changes they were fine with. And intents are composable, so that the intents that go to the 0x solvers, and the intents that go to a Starknet solvers, and the intents that go to the OpenSea solvers, I can build applications that reason through all of them. Like, I can build a new application on top of all these different kinds of intents. And maybe here, actually, I should have said this in the beginning, intents are just code. An intent is just a predicate over some state change. It is some code that gets run to say whether you're fine with a future state change. So they're fully programmatic. They can be arbitrary. Whatever you can write, you can express this as an intent. This allows you to do trades like, I am willing to sell Bitcoin for ETH if the weather is nice in Seoul, and if the weather is bad in Seoul, I'm willing to get ETH Classic. Things like this. Or you're willing to get different rates. They are fully programmatic. As long as you can express it within the gas bounds, you can create this as an intent. And yeah, then in the final step, transactions are then settled on a settlement layer. This kind of intent-centric design is necessary to enable decentralized counterparty discovery. And this is curiously where everyone is currently ending up anyway, where OpenSea is sort of a specific implementation of this pattern, of this design pattern. So 0x, so is Starknet, so is Optimism. What the Anoma architecture really does, it generalizes this pattern. People have intents. We want to then take multiple intents, run some decentralized compute over those intents, and then settle them on-chain. And this leads to this declarative paradigm for decentralized applications, where instead of authorizing execution traces, you authorize specific state changes, which honestly is probably going to be a must for like mass adoption, simply because like my parents can very easily reason through, I'm authorizing to hold some less Bitcoin if I hold some more ETH. They will never be able to reason through, I'm authorizing these 5 contract calls to get me the thing that I need. Right, and Anoma this results also that it's a black box architecture. Users author and submit intents, then magic happens, where the system figures out how to satisfy as many intents as possible, and then users just need to check the updated state. Users never have to worry about what the black box actually does, because they've authorized what they're okay with. I won't go through all of this, but very briefly, this is sort of the high-level overview of the architecture of Anoma. On the far left, you have counterparty discovery. And counterparty discovery is effectively users have intents. Those could be transparent, shielded, or private. Then the client generates some intent. This may involve the generation of a bunch of zero-knowledge proofs, or even the use of fully homomorphic encryption, but that's still further out. Then they submit these intents to the intent gossip network. Solvers can look at all intents, albeit that is going to be very hard. Generalized solving is most likely NP hard, and hence we aren't going to see generalized solvers for a long time to come. Practically speaking, what's most likely going to happen is that solvers pick a subset of intents that they care about, as in they select, maybe they're only interested in fungible token traits, and then try to compute solutions for that. So then solvers now compute a solution. Maybe they take 5 intents that are settable on chain. There are also incentives for intent gossip and so on. And solving, at that point, these could be front-run, right? Because it's way cheaper for me to say, oh, I look at someone else's solved intent cycle and I resubmit it myself. So all in the consensus part, solvers actually, all transactions are encrypted against a DKG, against what we're calling Fervio. It's a single shared public key controlled by the validator set. All transactions are encrypted against this, then submitted to the mempool. The mempool just establishes an ordering over arbitrary byte strings. At that point, then in block N, those arbitrary byte strings are fixed into a total order. Then you run consensus. Now you have a finalized block with encrypted byte strings. In the next step, then, in the next block, so at N+1, the validator set jointly decrypts all those encrypted transactions. At this point, everyone can see them in clear text, but they can't front-run, back-run, or sandwich them anymore because the ordering has already been established, and then they just execute them. The nice thing is you also don't have problems with commit-reveal schemes where you need economic incentives for people to reveal their transaction data, like the unencrypted text, because the validator set can just decrypt them themselves. And then in the last part, you get into execution and verification, where it comes to the unified execution environment that can handle transparent, shielded, and private state, and validity predicates, which is effectively then all state changes are applied, and all validity predicates are invoked, and all verifiers are invoked to verify the zero-knowledge proofs. And then in the end, users just check whether their thing got settled or not. OK, I want to take the last bit to talk about homogeneous architecture and heterogeneous security. Generally speaking, protocols can be benevolent monopolies. As in, everyone wins from agreeing on the same protocol. Everyone wins from agreeing to use TCP/IP. There are some improvements we could be making to TCP/IP, but the counterfactual losses are really marginal. Like, there may be a slightly better version of TCP/IP that we could be building, but there's a massive benefit in standardization. However, also, to make this more tangible, this is what allows mobile phones to work. Like, I bought my phone in Europe, and my phone works on the cellular backbone in North America and in Asia. It's magic, right? Like, you take your phone and it just magically works. It's because we agreed on the protocol for the cellular backbone. But importantly, security domains shouldn't be monopolies because they can extract rent, they can steal funds, they can freeze funds, and different people fundamentally will have different preferences to what security domain they're comfortable with. Maybe some people really want to hold all their assets on global Ethereum, and that is totally fine, right? That should be their choice. Maybe they consider this to be the most secure. But maybe someone else that lives in a village of 200 people that they've lived with for 200 years wants to hold all their assets in a security domain that's controlled by the people in his community. And that's also fine. We should just make sure that all these different security domains are interoperable. So if you have the same architecture but heterogeneous security, you can enable this where your phone can roam between different security domains without losing sort of the benefit of having a homogeneous protocol. Right, and this leads to separate protocol and architecture from the security model. This comes then to the deployment patterns of Anoma. So Anoma as an architecture can be deployed as an L1, so that's a globally sovereign chain. It can be deployed as a community operated chain. Maybe the people in Seoul want to run all their local commerce, and that's fine, right? That's a different security zone for deployment. You can deploy this as an L1.5, where you use Anoma to decentralize a specific L2. for example, like Starknet or Optimism or Arbitrum, where you just focus on decentralizing the intent, gossip, and solving part. Or you deploy this as a fully as an L2, where even the underlying settlement happens on Ethereum. And actually, in that case, you end up deploying the unified execution environment as to Ethereum. Right, so yeah, the first case was you can use intent gossip network only, you sequence and settle elsewhere. Or the second one is you decentralize also the solvers, not just the gossip, but you also decentralize the solvers. This you can do to like decentralize things like CowSwap or 0x. Yep. Or you can deploy Anoma as a fractal instance. Right. So what components do dApps on Anoma have? They have intent formats, as in everyone has to agree on the on a standard for the intents. They have solver algorithms that can look at multiple intents and combine them, and then they have validity predicates which provide settlement invariants that users care about. This is, for example, settlement invariants that the protocol as well as users care about. For example, this is the invariant that if you have Bitcoin floating around in the system, Anoma can't create new Bitcoin. So the settlement invariant of a Bitcoin transaction on Anoma needs to include the fact that no Bitcoin can be created or destroyed. This kind of vertically integrated architecture means that you get end-to-end security, liveness, and privacy guarantees that you can reason through. And that your applications are portable across different security domains, resulting in not having vendor lock-in. Yep, so what can you build with Anoma? Well, you can build a bunch of existing dApps, but with full stack decentralization. So fungible tokens like 0x and CowSwap, non-fungible token trading like Wyvern or OpenSea or AMMs. You can decentralize rollups using Anoma. You can decentralize the multisig that Gitcoin uses for public goods funding. But as I said earlier, when Ethereum was created, we also didn't know the entire scope of kind of applications that could be built in the long term. That only came after we had a generalized architecture that allowed a very novel thing to be done. So here are some ideas we're having on what you can potentially use Anoma for. So you can build private DAOs where the votes are private but the results are transparent. You can do private auctions, which is actually really cool because Anoma comes with programmable threshold decryption, meaning that transactions are encrypted against a single shared public key. This means that 15 people can come together and submit all their intents that are still fully encrypted, and then in 10 blocks, the protocol decrypts all those 10 or 15 intents, and at that point, you can run a solver algorithm that determines the sort of, let's say, the correct voting result or the correct auction result, or things like that enforces some fairness criteria between the different intents. Yeah, because you can. It's like if you think what CowSwap actually does, CowSwap enforces a fairness criteria that everyone gets the same price. And the way it works is, or the way you build this on Anoma is that all intents are first submitted to the chain. The CowSwap dApp on Anoma, or the CowSwap validity predicate, then says, well, a batch is 10 blocks. So after 10 blocks, protocol, please start decrypting everything in the previous 10 blocks. Now we have a batch of decrypted and available data that then solvers can look at it and go, I can't inject extra data because this is the batch, so you can't front run these batches anymore. And then the validity predicate on Anoma actually can see what is the best possible solution where everyone gets the best price. You can build private games, and I think the thing that I'm most excited about is multi-party, multivariate private bartering. Any asset can be traded for any other asset, and as long as you find some sort of path through maybe 500 different trades, you can get exactly what you want. And you don't have to worry on like figuring out exactly the 500 hops. Or you can build on-demand runtime rollups. Right, what is a rollup? A rollup is just you roll up a bunch of computation. If you have a state transition, if you have an intent A, B, C with state transitions A to B, B to C, C to D, you can just roll them up on the intent level, and you just get an on-demand runtime rollup. Yep, so Anoma is built by Heliox. These are my two other co-founders, Awa and Chris. Awa is running around here as well. We also have a booth upstairs. There are printed white papers, which aren't, no, actually, since today they're publicly available, but still, there's some copies with the updated white paper. You can also check out the entire team at heliox.dev/team. And yeah, thank you very much. Anoma is a unified architecture for full stack decentralization, and I hope you liked the talk.